Hello, welcome back to ZzScience. Tonight we're going to talk about something that happens very far away, something quiet in its own way, even though it involves more energy than we can really imagine. We're going to talk about stars colliding, not in the way you might picture it, not like two cars hitting each other on a highway. Stars don't crash that way. They don't have fenders or glass or metal that crumples. They're made of gas and light and gravity. When they come together, the story is slower, stranger, more patient than you'd think. And sometimes, the collision never quite happens at all. Let's start somewhere small. Imagine you're standing outside on a clear night. No moon, just stars above you, scattered across the dark like someone spilled salt on a black cloth. You might look up and feel small. That's natural. The stars are far away, much farther than our minds can hold comfortably. The light from some of them has been traveling for thousands of years just to reach your eyes tonight. But here's something else to consider. Those stars are moving, not quickly from our point of view. If you came back to the same spot tomorrow night, or next month, or even next year, the sky would look almost identical. The stars would be in the same places. The constellations would still form the same shapes. But they are moving. Every star in the sky is drifting through space, pulled by gravity, orbiting the center of the galaxy, responding to forces we can't see. Over thousands of years, the night sky changes. Over millions of years, it becomes unrecognizable. And sometimes, two stars end up on a path toward each other. Not by accident exactly, not by coincidence either, just by the slow, inevitable mathematics of gravity and time. Let's talk about binary stars for a moment. A binary star system is just two stars orbiting each other. They're more common than you might think. In fact, most stars in the galaxy aren't alone. They have companions. Partners. Sometimes those companions are close. Sometimes they're far apart, orbiting each other slowly over centuries. Binary stars don't usually collide. They circle each other, bound by gravity, like two dancers who never quite touch. They can do this for billions of years, longer than our sun has existed, longer than Earth has had oceans. But every now and then, something changes. Maybe one of the stars swells up as it ages. Maybe it becomes a red giant, its outer layers expanding, reaching toward its companion. Or maybe the two stars lose energy over time, spiraling inward, getting closer with each orbit. Gravity doesn't forget. It doesn't get tired. It just pulls, steadily, forever. And eventually, if the conditions are right, the two stars begin to merge. It doesn't happen all at once. When two stars finally come together, it's not an explosion, not at first. It's more like a slow blending. The outer layers of one star start to mix with the outer layers of the other. Gas flows between them. They share material, they share heat. From a distance, you might see the system brighten. You might see the light flicker or pulse as the stars interact. But you wouldn't see a sudden flash. You wouldn't see debris flying outward. Not yet. The process can take years, decades, longer. Stars are enormous. They contain more mass than we can easily think about. When two of them come together, they don't just touch and bounce apart. They sink into each other. They reshape each other. Gravity pulls them inward, toward a common center, and at some point, the cores meet. That's when things get complicated. Let's pause here for a moment. Stars are hot. You know that already. But the heat isn't just on the surface. It goes all the way down to the center, where nuclear fusion happens. That's where hydrogen atoms are crushed together so hard that they fuse into helium, releasing energy in the process. That energy is what makes the star shine. It's what keeps the star from collapsing under its own weight. When two stars merge, their cores come together, and if both cores are still burning fuel, still fusing hydrogen or helium or heavier elements, then suddenly you have twice as much fusion happening in one place. The temperature rises, the pressure rises, the star brightens. And sometimes, if the conditions are just right, the whole thing becomes unstable. There's a type of event astronomers call a luminous red nova. It's what happens when two stars merge, and the result is so bright, so energetic, that it outshines everything around it for a while. It's not quite a supernova, not quite an explosion, but it's dramatic in its own way. The star swells up. It glows red, then orange, then sometimes white. It throws off shells of gas into space, and then, over weeks or months, it fades. What's left behind depends on the stars. Sometimes you get a single, larger star, one that's hotter and heavier than either of the original two. It might burn brightly for a while, then settle down into a long, stable life. Other times, the merger doesn't quite finish. The two cores spiral around each other inside a shared envelope of gas, still separate, still distinct, but trapped together in a kind of cosmic waltz that might last for thousands of years. And sometimes, the result is something stranger. Let's talk about neutron stars. Neutron stars are what's left after a massive star explodes in a supernova. When a star runs out of fuel, its core collapses. The outer layers blow away into space, and what remains is a tiny, incredibly dense object made almost entirely of neutrons. A neutron star is about the size of a city, maybe 20 kilometers across, but it contains more mass than the Sun. If you could take a teaspoon of neutron star material and bring it back to Earth, it would weigh about 1 billion tons. Gravity on the surface of a neutron star is so strong that if you stood there, you'd be crushed instantly, flattened. Your atoms would be pressed together so tightly that you'd barely be thicker than a sheet of paper. Neutron stars are strange objects. They spin. Some of them spin hundreds of times per second. They have magnetic fields trillions of times stronger than Earth's. And sometimes, they're not alone. Sometimes, two neutron stars orbit each other. When two neutron stars circle each other, they release energy in the form of gravitational waves. Gravitational waves are ripples in space-time itself. They were predicted by Einstein more than 100 years ago, but we didn't detect them directly until 2015. The waves are tiny, unimaginably small. When they pass through Earth, they stretch and compress space by a distance smaller than the width of a proton. But we have detectors sensitive enough to measure them now. Detectors with laser beams that travel kilometers through vacuum tubes, bouncing back and forth between mirrors, watching for the tiniest change in distance. And in 2017, we saw something remarkable. Two neutron stars, orbiting each other in a galaxy 130 million light-years away, finally collided. The collision lasted about a second, maybe less. The two neutron stars had been spiraling toward each other for millions of years, losing energy, getting closer with each orbit. And then, in the final moments, they accelerated. They fell toward each other faster and faster, spinning around each other hundreds of times per second. And then they touched. The gravitational wave detectors on Earth recorded the signal. A chirp, they called it. A rising tone, like a bird's call, as the two stars spiraled inward. And then, suddenly, silence. The collision itself was too violent, too chaotic for the detectors to read clearly. But 2 seconds later, telescopes around the world saw something else. A flash of light. It came from the same spot in the sky where the gravitational waves had come from, a small galaxy in the constellation Hydra. The light was bright at first, then it changed color. It went from blue to red over the course of days and weeks. Astronomers had never seen anything quite like it. They called it a kilonova. When two neutron stars collide, they don't just release energy, they release matter, heavy elements, gold, platinum, silver, uranium. Elements that can't be made inside normal stars, no matter how hot they burn. These elements are forged in the collision itself, in the intense heat and pressure of two neutron stars tearing each other apart. And then they're scattered into space. The flash of light we saw was the glow of those newly formed elements, radioactive and hot, cooling down over time. It was beautiful in a way. Think about that for a moment. The gold in a wedding ring, the platinum in a piece of jewelry, the iodine in your thyroid. All of it came from events like this, from neutron stars colliding billions of years ago in galaxies we'll never see. The atoms in your body are old, older than Earth, older than the sun. They were made in stars and in the violent deaths of stars, and in collisions like the one we just talked about. You are made of stardust. That's not a metaphor, it's just physics. Let's slow down a little. We've been talking about collisions, about stars merging, about neutron stars spiraling together, about flashes of light and gravitational waves. But most of the time, space is quiet. Stars are far apart. Even in binary systems, even when two stars orbit each other, there's usually a lot of empty space between them. More space than you'd think. If you were standing on a planet orbiting one of those stars, you might look up and see the companion star in the sky. It might be bright, brighter than any star we see from Earth, but it would still be far away, still separate. You could spend your whole life on that planet and never see the collision coming. Because it would take time, thousands of years maybe, millions, longer than civilizations last, longer than species last. There's something calming about that, in a way. The universe moves slowly. It doesn't rush. Events that we think of as sudden or violent, like a supernova or a collision, are really just the final moments of processes that have been unfolding for ages. A star doesn't explode because it's angry. It explodes because it's run out of fuel. Because gravity has been pulling inward for billions of years, and now there's nothing left to push back. A collision doesn't happen because the universe is chaotic. It happens because orbits decay, because energy is lost, because gravity is patient. Everything in space happens according to rules. Slow rules. Predictable rules if you know how to calculate them. Let's talk about time for a moment. When we look at stars, we're looking backward in time. Light travels fast, faster than anything else in the universe. But space is so large that even light takes time to cross it. The light from the sun takes about 8 minutes to reach Earth. If the sun suddenly disappeared, we wouldn't know for 8 minutes. We'd keep seeing it in the sky, shining normally, until the last bit of light arrived. The light from the nearest star, Proxima Centauri, takes about 4 years to reach us. When you look at that star, you're seeing it as it was 4 years ago. The light from distant galaxies can take millions of years, billions of years. When we saw the collision of those two neutron stars in 2017, the light had been traveling for 130 million years. The collision itself happened long before humans existed, before mammals existed, back when dinosaurs were still evolving. And we saw it happen, in a way, all at once. There's something strange about that. The universe doesn't care about our sense of time. It doesn't care that we live for decades, not eons. It doesn't adjust its pace for us. But we can still watch. We can still build detectors and telescopes. We can still point them at the sky and collect the light that's been traveling for millions of years. We can still piece together what happened, even if it happened long before we were here to see it. In a way, we're witnessing the past, not reliving it, not changing it, just watching it unfold, slowly, one photon at a time. Let's come back to something simpler. You're outside again, looking up at the stars. Somewhere up there, two stars are orbiting each other. You can't see them, they're too far away. But they're there, circling slowly, year after year, century after century. Maybe they'll collide someday. Maybe they won't. Maybe they'll just keep orbiting forever, or at least until the universe changes in some way we can't predict yet. It doesn't really matter, does it? They're not in a hurry. Neither are we. There's a star system called ZzZscience. It's a binary system about 7,800 light-years away from Earth. Two stars orbiting each other closely. One of them is a white dwarf. That's the leftover core of a star that's already burned out and collapsed. The other is a normal star, still burning hydrogen, still alive in the usual sense. The two stars are so close together that the white dwarf is pulling material off the surface of its companion. Gas flows from the normal star onto the white dwarf, forming a disk of hot, glowing material in between them. Astronomers have been watching this system for a while now, and they've noticed something. The two stars are getting closer. Slowly, but measurably. They calculate that in about 100 years, maybe less, the two stars will merge. The white dwarf will sink into the normal star, or the normal star will be torn apart and pulled onto the white dwarf. Either way, the result will be violent. The system will brighten, dramatically. For a while, it might become one of the brightest stars in the night sky. Brighter than Sirius, brighter than anything except the moon. People will see it. They'll point at it. They'll wonder what it is. And then, over months or years, it will fade. That hasn't happened yet. It won't happen for a while. But the light from that future event is already on its way, in a sense. The stars are already moving toward each other. The collision is already inevitable, written into the physics of the system. We're just waiting for it to unfold. We're always waiting, really. That's what astronomy is. Watching, waiting, measuring, recording. Trying to understand what's happening in places we'll never visit, on timescales we can barely imagine. Let's shift gears a little. We've been talking about stars colliding, about binary systems, about neutron stars and kilonovae and gravitational waves. But what does it feel like to think about these things? I don't mean scientifically. I mean emotionally. When you sit outside at night and look up at the stars, knowing that some of them are moving toward each other, knowing that collisions are happening right now in distant galaxies, knowing that the light from those events might reach Earth someday, long after you're gone. What does that feel like? For some people, it feels lonely. The universe is big, really big, and we're small. We live on a planet that's just a tiny speck, orbiting a star that's just one of hundreds of billions in the galaxy, in a galaxy that's just one of trillions in the observable universe. It's easy to feel insignificant when you think about that. Easy to feel like nothing you do matters because the universe is so vast and so old and so indifferent. But here's another way to think about it. We're here. We exist. We're made of atoms that were forged in stars and scattered into space by collisions and explosions. We're standing on a planet that formed from the debris of earlier stars. We're breathing air that was made by living things that evolved over billions of years. And we're aware of all this. We can look up at the sky and understand what we're seeing. We can build telescopes and detectors. We can measure the light from distant galaxies. We can calculate the orbits of binary stars. We can predict when collisions will happen, even if they're centuries away. We're part of the universe, not separate from it. We're how the universe looks at itself. That's not a scientific statement, exactly. It's more of a philosophical one. But it's true in a way that matters. The universe is mostly empty space, mostly hydrogen and helium, mostly cold and dark and quiet. But here and there, in tiny pockets, something else happens. Stars form, planets form, life emerges. And sometimes that life becomes complex enough to ask questions, to wonder why the sky is dark at night, to figure out that the stars are suns far away, to discover that those suns are moving, changing, colliding. That's remarkable. It doesn't make the universe smaller. It doesn't make the distances any less vast. But it means we're not just watching the universe. We're participating in it. Let's talk about supernovae for a bit. A supernova is the explosion of a star. It happens when a massive star runs out of fuel and its core collapses. The collapse is so sudden, so violent, that it rebounds. The outer layers of the star are blown away into space at a significant fraction of the speed of light. For a few weeks, the supernova can outshine an entire galaxy. Then it fades. What's left behind is either a neutron star or, if the original star was massive enough, a black hole. Supernovae are important. They're how heavy elements get scattered into space. They're how iron and nickel and cobalt and all the elements heavier than helium get distributed through the galaxy. Without supernovae, there would be no planets like Earth, no rocky worlds, no metal cores, no life. But supernovae aren't collisions. They're the death of a single star. So why are we talking about them? Because sometimes a supernova can trigger a collision. Or rather, it can change the dynamics of a binary system in ways that lead to a collision later. Imagine two massive stars orbiting each other. They're both burning fuel, both stable, both going about their lives in the usual way. Then one of them explodes. The supernova releases energy. It throws off mass. Suddenly, the binary system is lighter. Gravity is weaker. The orbit changes. Sometimes, the two stars drift apart. Sometimes, they stay together, but in a new configuration. And sometimes, the shock wave from the supernova pushes the companion star inward, changing its orbit in ways that make a future collision more likely. There's a binary system called IK Pegasi. It's about 150 light-years from Earth. Two stars orbiting each other. One of them is a normal star, similar to the Sun. The other is a white dwarf. The white dwarf is slowly pulling material off its companion. Not much. Just a trickle of gas flowing from the normal star onto the surface of the white dwarf. Over millions of years, the white dwarf is getting heavier. And there's a limit to how heavy a white dwarf can get. It's called the Chandrasekhar limit, after the physicist who calculated it. About 1.4 times the mass of the Sun. If a white dwarf gets heavier than that, it can't support itself anymore. The pressure inside becomes too great. The atoms are crushed together so tightly that something has to give. And what gives is the star itself. When a white dwarf crosses the Chandrasekhar limit, it explodes. Not slowly, not gradually. It detonates. The entire star undergoes runaway nuclear fusion in a fraction of a second. Carbon and oxygen fuse into heavier elements. The energy released is staggering, enough to blow the star apart completely. This is called a Type 1a supernova. Type 1a supernovae are important to astronomers because they're remarkably consistent. They all have about the same brightness. That makes them useful as distance markers. If you see a Type 1a supernova in a distant galaxy, you can calculate how far away that galaxy is, based on how bright the supernova appears. This is how we discovered that the expansion of the universe is accelerating. But that's another story. IK Pegasi won't explode anytime soon. The white dwarf is still pulling material off its companion, but it's a slow process. It might take millions of years for the white dwarf to reach the Chandrasekhar limit. By the time it happens, humans might not exist anymore. Or we might. We might be out there, scattered across multiple star systems, watching from a safe distance. Either way, the explosion will happen. It's already written into the physics of the system. Just like the collision in V Sagittae. Just like the merger of those two neutron stars we detected in 2017. The universe doesn't wait for us to be ready. It just unfolds, according to its own rules, on its own timeline. Let's slow down again. Sometimes, when we talk about space, we talk about numbers. Distances in light years, masses in solar masses, temperatures in kelvins. The numbers are big, bigger than we're used to thinking about. But they're just numbers. They don't really capture what it's like to think about these things. Here's a thought experiment. Imagine you could travel faster than light. I know you can't. The laws of physics don't allow it. But imagine you could. You get in a spaceship and you fly to a distant galaxy. One of the galaxies where we've detected gravitational waves from merging neutron stars. You arrive just in time to see the collision. You're far enough away that it's safe. You won't be vaporized or crushed or irradiated. You're just watching. The two neutron stars are tiny. Each one is only about 20 kilometers across, smaller than most cities on Earth. But they're bright, incredibly bright. They're glowing from the heat of their surfaces, from the energy of their magnetic fields, from the friction of the material spiraling inward. They're moving fast, orbiting each other hundreds of times per second. You can't even see them as separate objects anymore. They're just a blur, a ring of light, spinning faster and faster. And then, in an instant, they touch. There's no sound, of course. Space is a vacuum. There's nothing to carry sound waves. But you'd see the flash, a burst of light, so bright that it would outshine every star in the galaxy for a moment. You'd see the jets, beams of particles and radiation shooting out from the poles of the merged object, traveling at nearly the speed of light. You'd see the debris, shells of gas and dust, expanding outward, glowing red and orange and gold from the heat of the newly formed elements inside. And then, slowly, it would fade. The merged object would settle down. Maybe it would become a black hole. Maybe it would become a heavier neutron star. Maybe it would be something we don't have a name for yet. But the show would be over. And you'd be left alone in your spaceship, watching the afterglow, trying to process what you just saw. That's what it might feel like, if you could be there. But you can't. No one can. The distances are too great, the energies are too extreme. We're stuck here, on Earth, watching from billions of kilometers away, collecting the light and the gravitational waves, and piecing together what happened. And maybe that's okay. Maybe it's better to watch from a distance, safer, certainly, but also more patient, more thoughtful. When you're far away, you have time to think, time to calculate, time to understand. There's something meditative about astronomy. You spend years gathering data, measuring positions, recording brightnesses, calculating orbits, and then, slowly, patterns emerge. You start to see how things are connected, how stars are born, how they live, how they die. You start to understand that the universe is not random. It's not chaotic. It's just following rules. Rules we can learn. Rules we can write down. Rules we can use to predict what will happen next. But the universe is also full of surprises. Even when we think we understand something, nature finds a way to show us something new. Like the kilonova in 2017. Astronomers had predicted that neutron star mergers would produce heavy elements. They'd done the calculations. They knew, in theory, what should happen. But seeing it was different. Seeing the flash of light, seeing the color change over time, measuring the spectrum and confirming that yes, there's gold in that debris, there's platinum, there's uranium. That was new. That was proof. And it changed the way we think about the universe. Now we know where gold comes from. We know where the heavy elements in our bodies come from. Not from normal stars, not from the sun, from collisions, from violence, from the most extreme events the universe can produce. Here's a quiet thought. Every time you hold something made of gold, you're holding a piece of a collision that happened billions of years ago. The atoms in that gold were forged in the final moments of two neutron stars merging. They were scattered into space. They drifted through the galaxy for millions of years. They became part of a cloud of gas and dust. That cloud collapsed. It formed the sun. It formed the planets. And eventually, some of those atoms ended up in the object you're holding. They've been on a long journey. And now they're here, with you, for a little while. That's true for everything, really. The iron in your blood, the calcium in your bones, the oxygen in your lungs. All of it came from stars, from the lives and deaths of stars that existed long before the sun. You are made of recycled stardust. We all are. Let's talk about something a little closer to home. Our sun is not in a binary system. It's alone. It doesn't have a companion star. At least, not one that we know of. There are some theories that suggest the sun might have had a companion long ago, billions of years in the past. But if it did, that companion is long gone now, drifted away, lost to the galaxy. So the sun won't collide with another star. Not anytime soon, anyway. But it will still die. In about 5 billion years, the sun will run out of hydrogen to burn in its core. When that happens, it will start to change. The core will contract. The outer layers will expand. The sun will become a red giant, swelling up to a size that might reach all the way to Earth's orbit. Mercury will be swallowed. Venus will be swallowed. Earth might be swallowed too. Or it might survive, barely, as a scorched, lifeless rock orbiting a dying star. The sun will shed its outer layers. It will throw them off into space, forming a beautiful, glowing shell of gas called a planetary nebula. And what's left behind will be a white dwarf, a small, dense core, about the size of Earth, slowly cooling down over trillions of years. That's the sun's future. Not a collision, not an explosion. Just a slow, quiet death. Most stars die that way, actually. Only the most massive stars explode as supernovae. Only the rarest of stars end up in binary systems that lead to collisions. Most stars just burn out. They shine for billions of years, then fade. And that's okay. That's just how it works. There's something almost comforting about that. The idea that most things in the universe don't end violently. They just end. Slowly, quietly. The way a candle burns down to nothing. But let's come back to collisions, because that's what we're here to talk about. When stars collide, something new is created. A new star sometimes. A heavier star. A brighter star. Or a neutron star. Or a black hole. Or a cloud of debris that will eventually become part of a new generation of stars. Nothing in the universe is really destroyed. It just changes form. The atoms are still there. The energy is still there. It's just rearranged. There's a concept in physics called conservation of energy. It means energy can't be created or destroyed. It can only change from one form to another. When stars collide, the kinetic energy of their motion gets converted into heat, into light, into the energy of nuclear fusion, into the gravitational potential energy of the merged object. The total amount of energy stays the same, it just moves around. The same is true for matter. Matter can't be created or destroyed either. Not really. It can change form. Hydrogen can fuse into helium. Helium can fuse into carbon. Carbon into oxygen, and so on. But the atoms are still there. The protons and neutrons and electrons are still there. They're just arranged differently. This is a long way of saying that nothing is ever really lost. When stars collide, they don't disappear, they transform. And the universe keeps going. Let's think about time again. We've talked about events that happened millions of years ago, billions of years ago. We've talked about events that will happen millions of years in the future. But what about now? What's happening right now, somewhere in the universe? Right now, somewhere, two stars are orbiting each other for the first time. They've just formed from the same cloud of gas. They're young, hot, bright. They don't know yet that they're bound together, that they'll spend the next billion years circling each other. Right now, somewhere, two stars are in the final moments before a collision. They're spiraling inward, faster and faster, releasing gravitational waves, heating up, brightening. In a few seconds or a few hours, they'll merge. Right now, somewhere, a neutron star is forming. A massive star has just exploded. The core has collapsed. The shockwave is still traveling outward, carrying debris and energy and newly formed elements. And at the center, a tiny, dense object is spinning, adjusting to its new form. Right now, somewhere, a white dwarf is slowly accumulating mass from its companion. It's getting heavier, year by year, century by century. It doesn't know yet that in 1,000,000 years, or 10 million, it will cross the Chandrasekhar limit and explode. It's just doing what white dwarfs do. All of this is happening right now. Not here, not in our solar system, not even in our galaxy necessarily, but out there, somewhere, in the vastness of space. The universe is big enough that everything that can happen is happening somewhere. And we're here, on Earth, watching, listening, building detectors to catch gravitational waves, building telescopes to collect light from distant galaxies, writing equations to describe what we see, trying to understand. That's what ZzZscience is about, in a way. Not just the science itself, but the experience of thinking about it. The experience of looking up at the night sky and realizing that you're seeing things that happened long ago. The experience of knowing that stars are colliding right now, even if we can't see it yet. The experience of being small and temporary and still somehow connected to all of it. Let's talk about light again. Light is strange. It's both a wave and a particle. It travels at a fixed speed, about 300,000 kilometers per second. Nothing can go faster. When light leaves a star, it carries information. Information about the star's temperature, its composition, its velocity, its age. All of that information is encoded in the light, in the brightness, in the color, in the way the light flickers or stays steady. When we look at a star, we're not just seeing a point of light, we're decoding information. We're learning about a place we'll never visit, a place that might not even exist anymore by the time the light reaches us. That's what astronomy is. It's detective work, piecing together stories from fragments of light that have been traveling for millions of years. And sometimes, those stories are about collisions, about stars that came together, merged, transformed, about energy released, about elements created, about gravity and time, and the slow, patient mathematics of the universe. Let's think about silence for a moment. Space is silent. There's no air, no medium for sound to travel through. If you were floating in space, near a collision, you wouldn't hear anything. You'd see the light. You'd feel the radiation if you were close enough. You'd see the debris expanding outward, but you wouldn't hear a sound. And yet, in a way, we can listen. Gravitational waves are sometimes called the sound of the universe. They're not sound waves. They don't travel through air. They travel through space-time itself. But when we convert the signal from gravitational wave detectors into sound, into something our ears can process, we hear a chirp, a rising tone. The sound of two massive objects spiraling together. It's beautiful in its own way, haunting. You can find recordings of these gravitational wave signals online. They're short, just a second or two, but they represent millions of years of orbital decay. Millions of years of two neutron stars slowly spiraling toward each other. All compressed into a single moment, a chirp, and then silence. Sometimes, the best way to understand something is just to listen, not to think about it, not to calculate it, just to listen. To let the sound wash over you. To feel the strangeness of it. There's a question people sometimes ask. If a star explodes in a distant galaxy and there's no one there to see it, did it really happen? It's a philosophical question, a variation on the old "if a tree falls in a forest" thought experiment. And the answer, scientifically, is yes. Of course it happened. The light traveled through space. The gravitational waves rippled outward. The debris expanded. The heavy elements were scattered. It all happened, whether we saw it or not. But there's another way to think about it. In a way, the event doesn't become real for us until the light reaches us, until we detect it, until we measure it, until we write it down. Before that, it's just a possibility, a prediction, a set of equations. After that, it's data, it's evidence, it's part of our understanding of the universe. This is true for everything, really. The past is always a reconstruction. We don't experience the past directly. We can't. It's gone. We only experience the light from the past, the signals, the echoes. And we piece together what happened based on those echoes. That's what we're doing when we study stellar collisions. We're piecing together stories from echoes, from light that's been traveling for millions of years, from gravitational waves that stretched and compressed space-time by less than the width of an atom. We're trying to understand what happened in places we'll never see, at times we can barely imagine. And somehow, we're succeeding. Slowly, imperfectly, but succeeding nonetheless. Let's talk about beauty. Is a stellar collision beautiful? It's hard to say. Beauty is subjective. It depends on the observer. But there's something compelling about the idea, isn't there? Two stars, orbiting each other for millions of years, getting closer, merging, releasing energy, creating new elements. It's violent, it's destructive, but it's also creative. It's how the universe makes heavy elements. It's how gold is formed. It's how new stars are born from the debris of old ones. There's a kind of beauty in that cycle. Birth, life, death, rebirth, over and over across billions of years. Artists sometimes try to capture this. You might have seen illustrations of neutron stars colliding, digital paintings, animations. They're often dramatic, bright colors, explosions, jets of energy shooting outward. They're beautiful in their way, but they're also interpretations. We don't have photographs of neutron stars colliding. We can't. They're too far away, too small, too fast. What we have are measurements, data points, numbers on a graph. The beauty is in the interpretation, in the story we tell ourselves about what those numbers mean. And that's okay. Science is about understanding, but it's also about storytelling. We take the data and we weave it into a narrative. We say, here's what happened, here's why, here's what it means. And in doing that, we make the universe a little more comprehensible, a little less alien. Let's come back to Earth for a moment. You're still outside, still looking up at the stars. It's late now, quiet. The air is cool. You think about everything we've talked about. Stars colliding, neutron stars merging, gravitational waves, kilonovae, white dwarfs accumulating mass. All of it happening out there, somewhere, right now. And here you are, standing on a planet made from the debris of earlier stars, breathing air made by plants that evolved over billions of years, looking up at a sky full of light that's been traveling for years, decades, centuries. You're part of all this, not separate from it, part of it. The atoms in your body came from stars. The light you're seeing came from stars. The gravity holding you to the ground is the same force that pulls stars together, that causes collisions, that shapes the universe. It's all connected. There's a word astronomers sometimes use, cosmic perspective. It means stepping back, seeing the big picture, realizing that you're small, but also realizing that you're part of something vast and ancient and ongoing. It's a humbling feeling, but it's also empowering, because if you're part of the universe, then understanding the universe means understanding yourself. Let's think about the future. What will we learn next? Gravitational wave detectors are getting better, more sensitive. We'll detect more collisions, more mergers, more events we didn't even know were possible. Telescopes are getting bigger, more powerful. We'll see farther, deeper into space, deeper into time. We'll find new binary systems. We'll predict new collisions. We'll watch them happen in real time as the light reaches us. And someday, maybe, we'll go there. Not in our lifetimes, probably not for centuries, but someday. We'll build ships that can travel between stars. We'll visit distant systems. We'll see these events up close. We'll stand on planets orbiting binary stars and watch them merge. Or we'll send probes, robots, AI explorers. They'll go where we can't. They'll see what we can't see. And they'll send back the data. That's a long way off. But it's possible. The laws of physics don't forbid it. It's just a matter of technology, of time, of will. For now, though, we watch from Earth. We build detectors, We build telescopes, we collect data, we try to understand, and we tell stories. Stories about stars colliding, about neutron stars merging, about the universe unfolding according to its own quiet, patient rules. These stories matter, not because they change anything. They don't. The stars will collide, whether we understand them or not. The universe will keep expanding, keep cooling, keep changing. But the stories matter because they help us make sense of our place in all this. They help us see that we're not alone. We're not separate. We're part of the universe. We're how the universe looks at itself. We're how it understands itself. And that's worth something. Let's talk about infinity for a moment. The universe might be infinite. We don't know for sure. The part we can see, the observable universe, is finite. It has an edge of sorts, a boundary beyond which light hasn't had time to reach us yet. But beyond that boundary, there's more universe. How much more? We don't know. It might go on forever. If it does, then somewhere out there, infinitely far away, there's another Earth, another you, looking up at the stars, thinking the same thoughts. That's a strange idea, but it's mathematically possible if the universe is infinite and if matter is distributed randomly. In an infinite universe, every possible arrangement of atoms will occur, not just once, infinitely many times. So there are infinite versions of you out there, some almost identical, some very different, some looking up at stars colliding, some not. That's speculation, of course. We can't prove the universe is infinite. We can't visit those other versions of Earth if they exist. But it's fun to think about. It reminds us that the universe is stranger than we imagine, stranger than we can imagine. And that's okay. We don't need to understand everything. We can't. The universe is too big, too complex, too strange. But we can try. We can look up. We can wonder. We can ask questions. And sometimes we can find answers. Not all of them, not even most of them, but some. And that's enough. Let's slow down one more time. We've been talking for a while now. About stars, about collisions, about light and time and gravity, about the strange, beautiful, violent, patient universe we live in. It's a lot to think about, and if you're feeling tired, that's okay. This is a long journey we're on, a journey through deep space, through deep time. You don't have to stay awake for all of it. Sometimes, the best way to experience the universe is just to let it wash over you, to close your eyes, to let your mind drift, to fall asleep under the stars, knowing that somewhere out there, collisions are happening, stars are merging, neutron stars are spiraling together, white dwarfs are accumulating mass. The universe is doing what it does, and you're part of it. So rest. Let the thoughts settle, let the images fade. The stars will still be there when you wake up. The universe will still be unfolding, slowly, patiently, according to its own quiet rules. And we'll still be here, watching, learning, trying to understand. Thank you for joining us tonight. Thank you for listening to these stories from deep space, for thinking about stars colliding, about time and distance and gravity, about our place in all this. It means something that you're here, that you're curious, that you're willing to wonder. The universe is vast, but you're part of it. And that makes you vast too, in your own way. Sleep well, dream of stars, and remember, somewhere out there, right now, two stars are dancing together, slowly, patiently, waiting for the moment when they finally touch. Good night.